So Unit 6 introduces our very first real set of reactions, which are going to be focused on brominations or reactions that are going to add bromines to our molecule. And one of the main ways in which we do this is through radical chemistry. A radical is a reactive intermediate, much like a carbocation or a carbanion. And this first video, we want to go through and kind of talk a little bit about the differences between these different reactive intermediates. Now, a reactive intermediate is a higher energy state than our reactants and products. Um, and they're these kind of like quasi short-lived states that are going to help us lead to our eventual products. And there's going to be these three main reactive intermediates that we're going to talk about. Our carbocations, those are going to be carbons that have a positive charge. We saw those when we were talking about resonance. Radicals, which we're introducing now, and then carbanions, which are going to be carbons that have a lone pair and a negative charge. We also saw that in both resonance as well as in our acid-base chapters. Now, there are some distinct differences between these, and for both the carbocation and the radical, these are known as electron deficient species. Carbocations will have 6 electrons, radicals will have 7 electrons around them, meaning that they're going to be short of their full octet. That means that they want to be stabilized. They want to get an extra electron or two, depending which it is, to be able to get to that full octet state. Now, much like how when we think about the stability of like a conjugate base, that's a charged species after you remove a proton, resonance and inductive effect were two important ways in which we stabilize those conjugate bases. That exact same thing will help stabilize our carbocations and our radicals. Now, much like when we were thinking about like distribution of charge, rather than having a carbocation sit on a single carbon, being able to spread it across multiple different carbons is good. And then especially in terms of the inductive effect, there's a difference between like a primary, secondary, or tertiary carbocation. As you start to put more and more stuff around it, that becomes more stable because you're pushing more electron density into it via the inductive effect. And these are all ways to help stabilize. Now, both carbocations and radicals are going to have a sp2 hybridization, meaning that they're going to have a trigonal planar geometry, and that's often going to result in a loss of stereochemistry for our reactions. And we're going to see that when we do our brominations. If there was stereochemistry at the point of where that bromine is going to be added, it's going to form that racemic mixture, or the mixture of R and S stereoisomers, which is ultimately going to result in a net loss of your stereochemistry. Now, carbanions on the opposite side are going to be electron rich. These are going to be 8 electrons around that carbon carrying a negative formal charge. Because of that, you'll have 4 domains which are going to be an sp3 hybridized tetrahedral geometry. And these are going to be very opposite. You already have a lot of electron density around it, so you do not want to have like a bunch of extra things around it. And we have kind of a table below here that kind of summarizes a lot of the kind of main differences between these. So we have our reactive intermediate of our carbocation, radical, and carbanion. In terms of our chemical structure, our carbocation is going to be a carbon that has some attachments at a positive charge. So here we see that there are 6 electrons rather than our ideal 8, 2 electrons per bond. A radical is going to be the same general setup, but you're going to have just a single dot making 7 electrons. Each dot represents a electron. So when we think of a lone pair, that is 2 electrons. Here, this is just a single electron, and that is known as a radical. A carbanion is going to be a carbon that has a lone pair and therefore a negative formal charge, and that gives you 8. So you can see the differences here between 6, 7, and 8 electrons between our carbocation with a positive formal charge, radical no formal charge, and carbanion with a negative formal charge. All of these are intermediates and are not super stable. Now your carbocation and your radical are going to be similar. These are both going to be electron deficient. Your carbocation is going to be your electrophile most of the time, and these are going to be more acidic. These are going to be things that are going to be accepting lone pairs when we think about like Lewis acid, Lewis base just definitions. In terms of stability, they want as much stuff around them as possible. So tertiary or the 3 degrees are going to be the most stable, where like primary is going to be rather poor. Your carbanion, on the other hand, has the exact opposite. It would much prefer something like a primary rather than a tertiary, because these are going to be nucleophiles. They're going to be things that are attacking. They're going to be strong bases. And if they have a bunch of stuff around them, it hinders their ability to be able to be a very good base. Now, you have a good feeling for how to do resonance with carbocations. Generally, you'll have an adjacent double bond or a lone pair that you're going to push into that positive charge. For carbanions, you're going to start with that carbanion and then have a double bond adjacent, which you're going to push into it. Radicals are going to be a little bit more unique, so let's go and take a quick second and focus on how we do resonance with radicals. Now I have this kind of already drawn out to kind of show here. So whenever we have a radical, we'll just do a single dot. So like on our original structure here, we see that we have a radical on that far end of our molecule. And we see one bond away, there is a double bond. And this is going to be the same kind of setup that we see in all of our other resonance cases. We have an intermediate, and then one spot away, we have a pi bond. These electrons that are highlighted, and technically also this one is also technically examples of electrons that are delocalized. They're not stuck on a single atom, they're able to move. And here we can do a series of curved arrows to be able to show the movement of electrons. Now, unlike the case of your carbanions and your carbocations, we are actually going to have 3 arrows associated with each movement from like step to step in your resonance, like different contributors. So 2 of them are going to be coming together to make a bond, and 1 of them are going to be going out to make your radical. Now, in terms of our movement of our arrows, normally when we've been showing arrows, we've been showing double barbed arrows. And a double barbed arrow is one that has 2 points at the arrow tip, and that corresponds to the movement of 2 electrons. A single barbed arrow is showing the movement of 1 electron. So you don't have that extra barb there. Now we're showing radicals, so all of our arrows here are all going to be these single barbed arrows. So for this, much like how we have like a carbocation, you're going to kind of get that swap between that double bond and that radical. But this is going to be shown by a total of 3 arrows rather than just 1. Normally with our carbocation, you just have that double bond fill that positive charge. Here, you're going to have the radical do a single barbed arrow to go into the bond, which is it is adjacent to, and then the double bond is going to have 2 double barbed arrows kind of going in opposite directions. One of them is going to go to the bond between it and the radical, and that's going to be making a double bond. We get 1 electron from the radical and 1 electron from the double bond. That's going to give us 2 electrons, and those 2 electrons we're going to see here as a double bond in the product, as I've just drawn here are highlighted in blue. Now that last electron, which still remains in the double bond, are going to go to the opposite side and become a radical up on the top there. So you are going to show that with 3 movements. Your radical and 1 electron from the double bond come together to make a new double bond, and then that 1 remaining double bond electron is going to go to the opposite side carbon to make a radical. And if there are further adjacent double bonds, so like we see here in this next one, we see there's another double bond, 1 away from that radical. We can do that same process again. And then directly below, just to avoid it being a little bit messy, I show that same process. You have your radical coming into the bond, double bond coming over, and then the remaining one going to a radical. Now, whether or not those arrows are on top or bottom doesn't truly matter. We'll often just kind of show it away where it kind of like has that nice like smooth flow, but if you draw them both, like for example, if you have a radical and a double bond, show that a little bit better, and you wanted to show like this one come here and this one comes there and that one goes like that, that's totally fine. They're both going to the same spot. They don't have to be one below and one above or something of that sort. Um, Now, there is one extra kind of unique thing we think about in terms of stability that I do want to go ahead and formalize. Generally, we've been talking about the differences between our primary, secondary, and tertiary. Our very first case is an example of a primary carbocation or primary radical. So we call this a primary radical here because there is just one thing that is bond to. It's all the way at the end. So there's just one bond. All of these other ones here are all examples of your secondary radicals because there are two things. And then if we had a tertiary radical where you'd have three bonds, where's radical? You would see a structure like that. And that's our primary, secondary, and tertiary. We talked about that when we were thinking about like carbocations. And for example, that tertiary radical is going to be more stable because it has more stuff around it. And that extra stuff is providing some inductive effect to help stabilize. There are two extra terms of benzylic and allylic that I want to formally define here. And these benzylic and allylic spots are going to be even more stable than our primary, secondary, and tertiary. And the definition for these are really just the ability to be able to undergo resonance. So an allylic, whether it's a carbocation or a radical, is going to be a spot that's going to be one away from a double bond. And that means that we're able to undergo resonance. So these are going to be more stable because you're actually able to physically move that intermediate. You then also have a benzylic, which we'll go ahead and show here in pink. And that's going to be one away from a benzene ring. That is specifically going to be a six-membered ring with a bunch of double bonds. If it is just a cyclohexane ring, it is not called benzylic. Benzylic does mean that we have that benzene ring itself. And this benzylic is actually going to be even more stable than the allylic because there's going to be three double bonds, which we can do resonance with compared to just one. So the benzylic and the allylic are going to be these like super stable structures that are going to be even more favored. And naturally, you can also have, a little bit more beyond just these two that we have seen here. So both of these are actually secondary radicals. So that is a secondary benzylic and a secondary allylic. You could have, like, for example, a tertiary allylic, and that tertiary allylic will be even more stable than your secondary allylic or your primary allylic. So these fit in with those same terms, but go even beyond that in terms of the fact that you have the ability of both inductive and resonance. And that's kind of a snapshot on a little bit of our reactive intermediates with radicals. We'll get a little bit of practice with these in class. And then in the next one, we'll jump into actually doing reactions with our brominations.